In last class we have seen z-test. Today we will see t-test. Z-test is based on normal distribution. T-test is based on students t-distribution. T-distribution is similar to z-distribution. T-distribution is a member of continuous probability distributions. T-distribution arises when estimating mean of normally distributed population when sample size is small and the population standard deviation is unknown. It was developed by William Seeley Gosset under the pseudonym Student. If we take a sample of n observations from normal distribution, then t-distribution with n-1 degrees of freedom can be defined as the distribution of the location of the sample mean relative to true mean divided by sample standard deviation after multiplying by the standardizing term square root n. Means t is x bar minus mu naught by s multiplied with square root n, which is very similar to z statistic x bar minus mu naught by s by square root n. Here in z statistic we will have sigma. Let's see what is degrees of freedom with simple example. Suppose average of 5 numbers is 3. If given equation is 10 plus x by 5 equal to 3, here x must be 5. Variable x do not have any freedom to vary. Suppose equation is like this: x1 plus x2 plus x3 plus x4 plus x5 by 5 equal to 3. Here x and mean are dependent on each other. So after estimating mean, we have only 4 independent choices for our sample of size 5. Let's see the definition. The number of degrees of freedom is the number of values in the final calculation of statistic that are free to vary. In this case, here degree of freedom is 4. Here degrees of freedom is 0. In general, the degrees of freedom of an estimate of parameter are equal to the number of independent scores that go into estimate minus the number of parameters used as intermediate step in the estimation of the parameter itself. Means suppose you have n observations and you used k parameters, then degrees of freedom will be n minus k. Most of the time, sample variance has n-1 degrees of freedom since it is computed from n random scores minus only one parameter estimated as intermediate step, which is sample mean. Here, this is already estimated. This is the k value here. So, sample variance has total n minus, here k is 1, so minus 1. X bar is estimated from sample, so degrees of freedom is n-1. T-distribution is symmetric and bell-shaped like normal distribution but has heavier tails than the normal distribution. See here, this black curve is the standard normal distribution. All other remaining curves are T-distribution curves with different degrees of freedom. We have seen this kind of distributions while we were discussing sampling distribution. When we roll one die, when we roll 2 dice, 4 dice, some n dice, then the greater the sample size, the more probability distribution of average values clustered around the center. But if you just roll 2 dice, then distribution was like this. If n number of dice rolled, distribution will be like this. Means when sample size is small, more tail area will be there, but when sample size is large, then tail area is very small. Like that, here also if sample size or degrees of freedom is small, the distribution has more tail area. For degrees of freedom 1, T distribution will be like this, yellow curve. For degrees of freedom 5, T distribution will be like this, blue curve. This blue curve has lower tail area than this yellow curve. If degrees of freedom more than 30, then curve will be similar to this standard normal curve, this black thick curve. You can see here the comparison of T distribution with Z distribution based on degrees of freedom. For degrees of freedom 1, curve is like this, red one. This blue curve is standard normal distribution curve. If degrees of freedom increasing, T distribution is approaching normal distribution. See here this red line is almost same as this blue line, that is the Z distribution curve. Means here degrees of freedom is 30. If degrees of freedom greater than 30, T distribution and Z distribution will be almost similar. Let x1, x2 and so on xn are drawn from normally distributed population with mean, mu and variance sigma square. Let x bar is sample mean and s is sample standard deviation. Then random variable x bar minus mu by sigma by square root n has standard normal distribution, but random variable x bar minus mu by s by square root n, here s is the sample standard deviation, has student t distribution with n minus 1 degrees of freedom. This random variable generally denoted as z, this random variable denoted as t. The difference here is sample standard deviation s is used in place of population standard deviation sigma. In place of this sigma, if s is used, then this random variable will follow students t distribution. T-test, we have this 4 kind of t-tests. Z-tests are appropriate for comparing means under strict conditions like normality of population, and you should know the sigma value. Here also population standard deviation should be known. T-test is appropriate for comparing means under relaxed conditions. Here we don't need to know this population standard deviation. In all the tests you don't require this population standard deviations. Let's see this first one. One sample t-test. One sample t-test assumptions are the population variance is unknown and the population follow normal probability distribution, or the sample size is large, means n greater than 30. If sample size is large, irrespective of population distribution, sampling distribution will follow normal distribution according to central limit theorem. So you require any one of these conditions, either population should be normal distribution or n greater than 30, one will be sufficient. One sample z-test compare a population mean mu, which is estimated from sample mean x bar, with hypothesized mean mu naught, to check whether two means, this hypothesized mean and estimated population mean, to check whether two means mu naught and estimated population mean mu are significantly different. In one sample t-test, we use the test statistic t equal to x bar minus mu naught by s by square root n. Here x bar is sample mean, s is sample standard deviation, n is sample size. This random variable t follows student t distribution with n minus 1 degrees of freedom. Let's see one example. Manufacturer wants to test whether their M30 bolts properly manufactured or not. Properly manufactured means M30 bolts diameter should be 30 mm. He cannot test all the bolts, so he took sample of 6. From that sample mean, he want to estimate diameter of all bolts. His sample values are 30.02, 29.99, 30.11, 29.97, 30.01, 29.99, all are in millimeters. Here we have raw data, we need to calculate sample mean. If you calculate sample mean of these 6 values will be 30.015, that is the x bar, and standard deviation for this 6 values is 0.049. From the given data, mu naught is 30 mm and sample size 6. In hypothesis testing, first step, formulate null hypothesis and alternate hypothesis. Null hypothesis will not claim any difference between two population means. Here hypothesized mean is 30 mu naught. Estimated mean mu will not differ with this mu naught, so null hypothesis will be mu equal to 30. Alternate hypothesis will be mu naught equal to 30. If you want 95% confidence level, alpha will be 0.05, means null hypothesis is rejected 5% of times when it is in fact true. Third step, find appropriate test to use and find the respective test statistic. Here we don't know the population standard deviation sigma, so you cannot perform z-test, but you can perform t-test if sample size greater than 30, but here our sample size is 6, this is less than 30, so let us assume population is normally distributed. Actually, we can estimate population normally distributed or not based on sample by using statistical tests like Shapiro Wilson test or by using QQ plots, but here we are not using any software, so let us assume population is normally distributed. So we can perform one sample t-test, then t-statistic will be x bar minus mu naught by s by square root n. Sample mean is 30.015, mu naught is 30 by sample standard deviation which was 0.049, so approximately it is equal to 0.05 by square root 6. If you calculate this value, t-statistic will be 0.75. The sample mean score, this 30.015 is 0.75 standard error units from this hypothesized mean value. Fourth step, find whether it is one tail or two tail test. Based on that, calculate critical value. Here it is two tail test. Find the critical value for 95% confidence level. T distribution will change based on degrees of freedom. Here degrees of freedom is sample size 6 minus 1, which is 5. Let's see the T table for critical value. Degrees of freedom, this is the degrees of freedom. Here degrees of freedom is 5. You have to see this row, and our test is two tail test, so see this row here, 95% confidence level, so this is our value 2.571. This is the T critical value for degrees of freedom 5 and 95% confidence levels for two tail test. If our test is one tail test, then you have to take the value from this column. Here our T critical value is 2.571. The table shown here is right half of the distribution. Since T distribution is symmetric, lower critical value will be minus 2.571. So T critical value for two tail test for 95% confidence at degrees of freedom 5 will be less or minus 2.571. Fifth step, compare T statistic with T critical value. Here T statistic is 0.75 and T critical values are 2.571 and minus 2.571. This T statistic do not falls in the critical regions, so result is not significant. If T statistic falls outside confidence interval range or within the rejection region, you will say that result is significant. Here result is not significant, so this value is very likely within this null distribution, so we cannot reject this null hypothesis based on this evidence. And we can check by using p-values also. This method is not recommended when you are not using any software, because p-value calculation for T distribution will be difficult, because T distribution will be changing with degrees of freedom, so representing that entire table in one page will be very difficult. But we can estimate p-value from the given table. Let's try to estimate p-value. T statistic value is 0.75 and our degrees of freedom is 5, so you have to search this row, degrees of freedom 5 for p-value 0.75. Here it is 0.727, but here 0.9, so our value will be between these two values and very close to this 0.727, means it might be somewhere here. Here probability value is 0.25. If you calculate exact probability value for this t-score with degrees of freedom 5 in Python, that would be 0.24. But here test is two-tail test, so multiply that 0.24 with 2, then you will get two-tailed p-value, that is 0.48. You have to compare this p-value with alpha. Here p-value 0.48 greater than alpha 0.05, means this blue region is more than the critical region, so we cannot reject null hypothesis, means results are not significant. T-test tells us that bolts are manufactured properly. you are unable to reject this, so you have to consider it is not right. Let's find 95% confidence interval. It is very similar to Z-test confidence intervals, but here critical value will be a little bit different. In Z-test, you have to search for the Z critical value based on alpha. Here, with alpha, you need to consider degrees of freedom. Since it is two-tailed test, so you have to see this lower row and degrees of freedom 5. So critical value is minus 2.571 and X bar is 30.015, S is 0.049, N is 6. If you calculate this value, lower bound would be 29.96358, 30.06642. This sample mean, this green dot 30.015, and this is the lower bound 29.96358. This is the upper bound 30.06642. Population mean mu naught 30 between this confidence interval range, so you cannot reject null hypothesis. Let's see another problem. Test the null hypothesis that the population mean is less than or equal to 5 with following data. Sample standard deviation S is 0.022789. Sample size N is 195. Sample mean X bar is 9.26146. Significance level alpha 0.05 means 95% confidence level. From the hypothesis statement, mu naught is 5. Null hypothesis H naught is mu less than or equal to 5. Alternate hypothesis H1 mu greater than 5. And significance level is 0.05. Find appropriate test and find the test statistic. Here we don't know population standard deviation sigma. Here sample size is 195, so sample will follow normal distribution. This is not necessary here. T equal to X bar minus mu by S by square root n. Sample mean X bar is 9.261460 minus mu naught 5 by 0.022789 by square root 195. T statistic value is 2614.392. Sample mean score 9.26146 is 2614.39. Standard error units from the population mean 5. Means it is too far from the expected mean value 5. We need to find whether it is one-tail or two-tail test. Here from this alternate hypothesis you can say that it is one-tail test, and that is again right tail. So find the T critical value for one-tail test. You have to see this row. Our sample size is 195, so degrees of freedom will be 194, which is not there here. Means after 120 values will be very similar to this row. So let's check this row, and it is one-sided test, so you have to check for this row, and 95% confidence level in this one tail, it will be 1.645. T critical value for one tail test for 95% confidence at degrees of freedom 194 is 1.645. T critical value is 1.645 and T statistic is 2614.39, which is too far from this T critical value, that too in the rejection region. So result is significant. So you can reject this null hypothesis by using p-values. P-value for 2614.392 will be less than 0.00001. If you see this table, here our degrees of freedom is 194, which is close to this 100. So you can check this row. But here probability value 0.0005, T statistic is 3.390. See here, T statistic value increasing, P value decreasing. Means if your T statistic is 2164 point something, then your probability value will be very less. Means you can consider which is less than 0.00001. This P value less than significance level 0.05. So results are significant. You can reject this null hypothesis. Means test tells us that the population mean mu greater than 5. If you construct confidence intervals, since it is one tail test, construct one tail confidence interval. We already seen critical value for 95% confidence level with degrees of freedom 194 for one tail test, which is 1.645, and substitute the sample mean, sample standard deviation and sample size. Then you will get upper bound and lower bound. Upper bound is 9.264141, lower bound is 9.258778. Since it is right tail test, you don't require this upper bound. You have to replace that with infinity. Let's assume 9 is here. The lower bound will be somewhere here. From here to this entire part is confidence interval range up to positive infinity. This 9.2614 is the sample mean, which is too far from the mu naught. This mu naught value 5, which is not in this confidence interval range, so you will reject null hypothesis. If you want more clarity on this confidence interval construction, see the video confidence intervals and one sample z test problems. We can get more clarity on this confidence intervals.